On January 27, 1922, Washington, D.C. operated under building codes and architectural practices shaped by decades of moderate mid-Atlantic winters. The city's commercial and public structures, many constructed in the late 19th and early 20th centuries, featured flat or low-pitch roofs designed primarily for aesthetic conformity and cost efficiency rather than significant snow load capacity. Standard engineering assumptions in the region rarely accounted for sustained accumulations exceeding 12 inches, as historical snowfall records indicated such events occurred infrequently. Theaters, markets, and assembly halls prioritized interior volume and unobstructed sightlines, often employing long-span truss systems with minimal intermediate support. Snow removal infrastructure consisted of manual labor supplemented by horse-drawn equipment, adequate for typical winter conditions, but not scaled for rapid clearing of heavy accumulations across extensive roof surfaces. The prevailing expectation held that intermittent warming periods or natural compaction would limit structural stress before critical thresholds were reached. Washington, D.C. in January 1922 contained a building inventory reflecting 4 decades of urban expansion. Structures erected between 1880 and 1920 employed cast iron columns, timber roof trusses, and unreinforced masonry bearing walls as dominant structural systems. The Knickerbocker Theater, completed in 1917 at 18th Street and Columbia Road, NW, exemplified contemporary entertainment venue design with a flat concrete roof, spanning 98 feet without intermediate columns to preserve audience sightlines. Roof construction typically utilized truss assemblies supporting decking of wooden planks or poured concrete slabs, with minimal redundancy in load paths. Building regulations in the District of Columbia specified live load requirements for roofs at 20 pounds per square foot, a standard derived from general occupancy considerations rather than climatic data specific to extreme snow events. Commercial districts concentrated structures of similar age and design methodology within limited geographic areas, creating zones of uniform structural vulnerability. Inspection protocols focused on fire safety and occupancy limits rather than seasonal load monitoring. Engineers of the period calculated snow loads using rules of thumb that assumed brief accumulation periods followed by melt or manual removal. The absence of weather forecasting systems capable of predicting multi-day snowfall duration meant that design decisions incorporated no provision for sustained accumulation scenarios. Flat roofs offered economic advantages in construction cost and urban land use efficiency, but provided no mechanism for gravitational shedding of precipitation. The prevailing assumption held that Washington's latitude and proximity to the Chesapeake Bay moderated winter severity sufficiently to prevent prolonged heavy snow events. A low-pressure system originating over the Gulf of Mexico on January 26, 1922, tracked northeastward along the Atlantic coast, drawing moisture from ocean surfaces warmed by the Gulf Stream. As the system approached the Chesapeake Bay region, it encountered a stationary high-pressure zone over the Great Lakes, which blocked continued eastward progression and forced the low to stall near the Virginia-Maryland border. This configuration established a persistent easterly flow that channeled moisture-laden air inland, while maintaining surface temperatures between 28 and 32 degrees Fahrenheit across the Washington metropolitan area. Snow began falling in the District of Columbia at approximately 1400 hours on January 27, with precipitation rates reaching 1 to 2 inches per hour during peak intensity periods. The storm's stationary nature prevented the typical passage pattern that limits accumulation duration in mid-latitude cyclones. Atmospheric soundings from the limited observational network available in 1922 indicated a shallow cold layer near the surface overlain by marginally warmer air aloft, producing snow crystals of high density rather than light, fluffy aggregates. Wind speeds remained below 15 miles per hour throughout the event, insufficient to cause significant drifting or redistribution, but adequate to prevent immediate settling of falling snow. The storm system's slow movement meant that bands of heaviest precipitation remained nearly stationary over the same geographic area for more than 18 consecutive hours. Temperature profiles remained within a narrow range that sustained continuous snowfall without transitional periods of sleet or rain that might have compacted or melted accumulated layers. By 2100 hours on January 27, official measurements at the U.S. Weather Bureau station in downtown Washington recorded 16 inches of snow accumulation, with continuing precipitation at rates exceeding 1 inch per hour. Snow density measurements indicated values between 15 and 20 pounds per cubic foot, substantially higher than the 6 to 12 pounds per cubic foot typical of powder snow conditions. This density translated to static loads approaching 25 to 30 pounds per square foot on horizontal surfaces after 16 inches of accumulation. Flat-roof structures received uniform loading across their entire surface area, without the load relief provided by pitched roofs where snow slides or sheds under gravitational influence. The wet, dense character of the snow caused immediate adhesion to roof surfaces, preventing any natural clearing mechanism. Buildings with parapet walls experienced additional accumulation, as these vertical barriers trapped snow that otherwise might have been transported by wind. Continuous precipitation through the evening hours added mass at a rate faster than sublimation, evaporation, or structural deflection could relieve. By 2200 hours, accumulation depths reached 28 inches in undisturbed locations, corresponding to static loads of 40 to 50 pounds per square foot, exceeding the 20-pound design threshold specified in local building codes. The absence of freeze-thaw cycles or rain events meant that the snow load consisted entirely of additive layers without consolidation that might have reduced total depth. Temperature conditions prevented any melting that would have reduced mass through drainage. The temporal pattern of accumulation allowed no recovery interval during which structural elements might have redistributed stress or undergone elastic rebound. At approximately 21:15 hours on January 27, the roof structure of the Knickerbocker Theater experienced catastrophic failure under snow load estimated at 48 pounds per square foot. The concrete roof slab, supported by steel trusses spanning 98 feet, deflected beyond its elastic limit as accumulated snow mass exceeded the combined capacity of the structural system. Initial failure occurred at truss connections, where tensile stresses concentrated in riveted joints and welded seams. Once primary load-bearing elements yielded, progressive collapse propagated as adjacent members received redistributed forces beyond their individual capacity. The roof assembly descended into the theater's balcony section, impacting occupants in a zone of approximately 2,000 square feet. The collapse sequence lasted fewer than 5 seconds from initiation to full structural descent. Engineering analysis conducted in subsequent investigations identified inadequate safety factors in the original design calculations, particularly in connection details where stress concentration effects had not been properly accounted for. The concrete slab's own dead load, combined with the snow surcharge, created bending moments that exceeded the flexural capacity of the supporting trusses. No partial collapse or warning deflection preceded the final failure, as the brittle nature of the connection failures prevented gradual yielding. Other structures throughout Washington experienced similar loading conditions, with numerous buildings sustaining roof damage or partial collapses in the hours following 2100 on January 27 and continuing into January 28, as snow accumulation reached final depths of 28 inches across the metropolitan area. Emergency response systems in Washington, D.C. on the evening of January 27 operated without centralized dispatch or motorized transport capacity. Fire and police services relied on horse-drawn apparatus and foot patrols, both severely limited by 28 inches of uncleared snow on roadways. Notification of the Knickerbocker Theater collapse reached authorities through telephone calls from survivors and witnesses, but deployment of rescue personnel required more than 40 minutes due to impassable streets. Hospitals received casualties transported by private automobiles and wagons, with patient arrival rates overwhelming available surgical capacity between 2,200 hours on January 27 and 200 hours on January 28. Telephone exchanges experienced circuit overload as simultaneous calls exceeded switching capacity, degrading communication between emergency services and medical facilities. Street railway systems suspended operations at approximately 1900 hours on January 27 due to snow depth exceeding track clearance limits, eliminating mass transit options for personnel attempting to reach incident sites. Snow removal equipment consisted of fewer than 20 motorized plows citywide, insufficient to clear priority routes within operationally relevant timeframes. Private citizens organized improvised rescue efforts at the Knickerbocker site using hand tools and debris removal by manual labor. The concentration of structural failures in commercial districts meant that multiple incident sites competed for limited response resources simultaneously. Weather conditions prevented aircraft observation or communication relay, restricting damage assessment to ground-level reports transmitted through degraded telephone networks. Hospitals exhausted blood supply reserves and surgical materials by 400 hours on January 28, requiring emergency procurement from regional facilities that could not be reached until rail lines were cleared on January 29. The Knickerbocker Theater collapse resulted in 98 confirmed fatalities and 133 injuries, requiring hospitalization. The theater contained approximately 300 occupants at the time of structural failure, with casualties concentrated in the balcony section, directly beneath the collapsed roof assembly. Additional building failures occurred at the Arcade Market at 14th Street and Park Road NW, where partial roof collapse caused no fatalities but rendered the structure unusable. The Ambassador Theater at 18th Street and Columbia Road sustained roof damage, requiring evacuation and closure. Residential structures throughout Washington experienced roof failures, with documented collapses affecting at least 12 single-family homes and 4 apartment buildings, resulting in 15 additional fatalities and 37 injuries. Total displacement exceeded 400 residents requiring emergency shelter. Commercial warehouse facilities in the Georgetown and Navy Yard districts sustained structural damage, affecting approximately 200,000 square feet of enclosed space. The snow load event produced structural losses across 114 documented buildings, requiring either demolition or major reconstruction. Casualty demographics reflected the evening entertainment schedule, with theater occupants ranging from adolescents to elderly patrons. Medical facilities treated crush injuries, fractures, and asphyxiation cases in proportions consistent with building collapse mechanisms. Property damage assessments compiled by municipal authorities estimated direct structural losses at $2 million in 1922 valuation. Insurance claim volumes exceeded the processing capacity of regional carriers, requiring intervention by federal banking authorities to prevent liquidity failures in the local insurance market. The District of Columbia Board of Commissioners convened investigative proceedings on January 30, 1922, to examine structural failures and review building code adequacy. Engineering consultants retained by the board conducted site inspections at the Knickerbocker Theater and 12 other collapsed structures, documenting design specifications, material properties, and failure modes. The investigation determined that existing code provisions specifying 20 pounds per square foot roof live load were insufficient for extreme snow accumulation events, and recommended revision to 40 pounds per square foot for flat or low-slope roofs. The American Society of Civil Engineers formed a committee in February 1922 to develop standardized snow load maps for structural design, incorporating meteorological data from the U.S. Weather Bureau's historical records. The District of Columbia revised its building code in June 1922, implementing increased snow load requirements and mandating structural plan review by licensed engineers for buildings exceeding specific occupancy thresholds. The Knickerbocker Theater site remained closed pending litigation over liability and negligence claims, with legal proceedings extending into 1924. Insurance industry organizations revised underwriting standards for commercial structures to require certification of snow load capacity in regions identified as moderate to high risk. The U.S. Weather Bureau expanded its observational network and initiated research into forecasting techniques for winter storm duration and intensity, with findings published in technical bulletins distributed to engineering professional societies. Congressional hearings in March 1922 examined federal building standards and recommended uniform application of updated load requirements across all government-funded construction projects. Documentation of the event contributed to the development of probabilistic load modeling methods that became standard practice in structural engineering by the mid-1920s.